Jonathan. So today I'm going to be talking about the work that I do studying the atmospheres of exoplanets, or planets outside of the solar system. And I'm really excited to talk about this because I like to think about it as studying the weather on other worlds. We know that a lot of the planets in the solar system have atmospheres and that they have clouds on them. And so when we think about planets outside of the solar system, I'm really interested in whether or not they have clouds on them, whether they have hazes on them. And if so, what are they like? So to actually set the scene for this question, I want to talk about the first exoplanet that was ever discovered. So this planet is called 51 Pegasi b, or 51 Peg b for short. It was discovered in the mid-1990s. And this is an artist's rendition of 51. So in our solar system, gas giant planets like Jupiter and Saturn are farther out. They're beyond the orbit of Mars. But this planet is actually so close to its host star that a year on this planet is 4 days. So that also means that this planet is very hot. Hence, we call planets like this gas giant planets that are very close into their host stars hot Jupiters. And since the discovery of this first planet, we have actually made enormous progress in the discovery of planetary systems. Today, we know thousands of planets that are out there. And not only that, but we know for the first time with certainty that there are more planets out there than stars. So with the discovery of knowing about all of these planets, the next chapter in exploring exoplanet systems has to do with understanding their atmospheres, characterizing what they're like. So how do we study exoplanet atmospheres? Well, one of the techniques that we use relies on studying exoplanets as they transit or pass in front of their host stars. So here I've got a schematic that shows a star, that's the yellow circle, the planet, which is the black disk, and then the surrounding ring, the surrounding blue ring, is the planet's atmosphere. When the planet passes in front of the star, it will block out a fraction of the starlight that is proportional to the size of the planet. And that's what this dip here is showing. This dip in the starlight is proportional to the size of the planet. So the transit method has been known as a really good technique for detecting whether or not planets are around different systems. But we can also use this technique in order to determine whether or not planets have atmospheres and what they're like. And to do that, we can observe planets when they transit at different wavelengths, because at different wavelengths, the size of the planet or the size of this dip varies. This technique is called transmission spectroscopy, and I've got a cartoon here that illustrates this effect. So on the left here, we've got the planet core, that's the black circle. The surrounding ring is the planet's atmosphere, and then we've got the star. The changing colors of the star correspond to observing the star at different wavelengths. And what we see is that depending on what wavelength we're looking at, the opacity of the planet's atmosphere can vary. It can either be more opaque or less opaque. So at wavelengths where the planet's atmosphere is more opaque, the planet appears larger. And so that is because at those wavelengths, absorption by atoms and molecules that are present in the planet's atmosphere occurs. So what I have here is a diagram of a planet's atmosphere, and the planet is being irradiated by its host star. So we can see the different atmospheric layers kind of extend out. Here's the planetary surface. And depending on what wavelength range we're looking at, we can see deeper into the atmosphere. So in the visible and the infrared wavelength ranges, we can see the deepest into the planet atmosphere. And from work that has been done in the past decade or so, we have found out that when we observe at optical wavelengths or at visible wavelengths, we can figure out if a planet has clouds or hazes in it. We can also detect signatures of absorption or fingerprints of sodium and potassium. If we observe in the infrared, we can detect even more fingerprints of absorption for water, for example, or carbon monoxide, methane, and carbon dioxide. And if we observe in the ultraviolet wavelength range, we're actually probing a little bit higher up in the atmosphere. So this upper atmospheric layers. And that's really important because it can help us kind of figure out if planets have atmospheres that are escaping or being blasted away due to radiation from their host stars. So this is going to be a very interesting designed telescope, and I want to tell you a little bit more about kind of the design or the structure of it. So this is the first surface that light from far away objects will hit when we observe with the GMT. This is called the primary mirror of the telescope. This mirror, the combined mirror, is going to have a diameter of 24.5 meters, so it will have roughly the area of a basketball court. And the unique part of this design is that it's made up of these 7 individual mirror segments. And these mirrors are a little over 8.5 meters in diameter, or just about 8.5 meters in diameter. And they're about the width of a tennis court. Each one of these segments will also weigh 17 tons, and it takes a couple years to finish them. So it takes 1 year to cast and cool the mirror, and then it'll take another 3 years to polish this mirror. And the reason why it takes so long is that we want to make sure that the surface of the mirror is extremely smooth and doesn't have any imperfections, so that we can obtain the best possible data using this telescope. So this is neat because the best and biggest telescopes that we have thus far are about 10 meters in diameter, or 6.5 meters in diameter. But the Giant Magellan Telescope is going to be 24.5 meters in diameter, so it's about 3 to 5 times larger and better than some of the current best facilities that we have now. So how is the GMT going to do this? So just as a reminder, telescopes are light buckets. This is how they work. They essentially just collect particles of light called photons, and so the bigger your bucket is, the more photons you'll collect. And so the same thing goes with the diameter of a telescope. In other words, if your telescope has a larger diameter, you'll collect more photons and in a given amount of time. And so this is great, but then we really need to understand this light. And in order to understand this light and to understand what it's made of, we actually need to split the light or disperse it into its colors. And that's why we need instruments mounted on telescopes, because instruments split the light that is collected by the telescope into its colors. So it will have the capabilities to observe these small planets, and we are going to use this capability in order to find these fingerprints of life. And one particular fingerprint that we're really interested in is this fingerprint for oxygen. So most of the work that I mentioned so far suggests that we're looking for fingerprints of sodium or potassium, but with GClef, we will be able to search for oxygen. And we're interested in oxygen because based on what we know about Earth and what is abundant in Earth's atmosphere, we think that oxygen would be a pretty good indicator for life on another planet. Not only can we do exciting science, answer some of the questions that people have been asking for centuries, is there life out there? Are we alone? We'll be able to, for the first time, detect oxygen if it is present in any atmosphere of any planets outside of the solar system. But it also represents an opportunity for me to be a part of this. It is very closely related to the work that I do, and it's something that I can be involved in very much in the near future. And so there's a lot of exciting things coming up, and there's a lot that I'm looking forward to. Thank you.